Hello, I need your help. I have here a university question which I think you guys could probably do and tell me where I've gone wrong, which is almost certainly absolutely everywhere. So I'm going to work through a question with you guys and tell me if I'm wrong, which is almost a certainty. So let's read the question. A supernova is observed in a galaxy. It says the number of the galaxy, doesn't matter, it's irrelevant. And the galaxy is at a distance of 51 megaparsecs away. In order to spatially resolve the supernova from the center of the galaxy, an astronomer needs to measure the precision of the supernova within the galaxy to a precision of 400 parsecs. To achieve this, they are using a ground-based telescope with a primary mirror diameter of 12 centimeters and a broadband filter centered on a wavelength of 1.2 micrometers. The seeing at the observatory is 0.75 arcseconds. Now, the way I approached this was to turn over and continue with a different question. No, that's not true. I managed to answer a bit of it, but I think I've got a method now and I'm going to go through that with you. I hope you guys can see everything. I've got a little tiny camera here, which is on my piece of paper, and I've already worked it out here, and I'm just going to go through everything. So the bits we know on this. So it says here that the supernova is a distance of 51 megaparsecs away. So we know our distance is 51 megaparsecs, so our distance d. And we also know that the precision required is 400 parsecs. Now I've considered the 400 to be the size of the object that they want to measure. So essentially I'm going to write down that the precision is going to be 400 parsecs. And we need to find, in the first part of this question, it says here, the angular precision, which will be theta. So we'll consider theta to be the angular precision that we require. Okay, so for this particular question, I'm going to draw a triangle. So I will draw a triangle like this, and this angle here is the one that we're trying to find. And we know that with a triangle, we've got our distance here, which is d, and that is 51 megaparsecs. And the precision here, I'm considering that to be 400 parsecs. I'm kind of hoping that I've used those figures correctly. Let me know if I haven't. Now, we know that distance, d, the size of the object, is 400 parsecs. That's the resolution we require. So we'll call that d is going to be theta times by the distance away. And with this particular calculation, I'm going to use the small angle approximation where sine theta is pretty much equal to theta when it's in radians and very, very small. So we're going to use the small angle approximation for that. So let's whack some figures into this particular formula. So I'm going to go the size here, the precision is 400 parsecs, and I'm going to put theta there, and that's going to be times 51 times 10 to the 6 parsecs, so that's 51 megaparsecs there. And when we rearrange this, we have theta 400 parsecs divided by 51 times, let's move this up so you can still see it, 51 times 10 to the 6 parsecs there. Now, if I plug that into my calculator, it should hopefully come out with the following. So 400, and then I need to go 51 times and 10 to the 6, and that should then transfer into decimal. So we now have theta is equal to 0.000784313, and that is in radians, and the answer asks this to be in arc seconds. So we now need to convert that value there into arc seconds. Now, according to my notes, the number of radians can be converted by using, so I should make that to times, sorry, I made a mistake there. So number of radians is times by 3,600 arc seconds times by 180 degrees divided by pi, and that gives us an answer in arc seconds. Would help if I could spell. So if I now convert this here, so we'll go 7.8 times 10 to the minus 6, because it's 1, 3, 4, 5, 6, times by 3,600 times by 180 degrees over pi, which gives us, let's put all of that into our calculator. So it's 7.8 times 10 to the minus 6 times by, huge bracket, then we need to go 3,000 times by 180 degrees, 3,600 times by 180 degrees, times by pi, close brackets, gives me 1.6 arc, actually it's 1.6 arc seconds. So I believe that is the answer to here, which says the angular precision in arc seconds to two significant figures is 1.6. So to two significant figures, that's 1.60, so it's only to the first two. So that is the angular precision required. I'm hoping that is correct. So that's the first part of our question. I'm going to put that to one side. The next part of our question is asking for the limiting angular resolution of our telescope. Now this is where a formula called the Rayleigh formula comes in. And the Rayleigh formula, again in radians, takes theta equals 1.22 times by the wavelength divided by the diameter of our telescope. Now we know some of this information because we are given it. So theta we are trying to find, and then the wavelength is given to us, and the wavelength is 1.2 micrometers, and we know the diameter of the telescope. The diameter is 12 centimeters. Now we need to obviously convert these into things that we can use, so that will be 1.2 times 10 to the minus 6 meters, and then we will also have 0.12 meters there as well. So we can whack these into this Rayleigh calculation to find out the actual limiting resolution of our 12 centimeter telescope. So let's put those figures in. Okay, so I've got those figures in there, and I'm now going to put them into the calculator. So we go to fraction 1.22 times by, I'm going to put that in a bracket just because I think it needs it, times 10 minus 6, close bracket, and divided by the 0.12, which is the diameter of the mirror. And that should give us an answer of 0.000122. So that's theta, and that's in radians. And again, we now need to transfer this from radians into arc seconds. So we go back to our arc seconds, so number of radians times by 360 arc seconds times by 180 degrees divided by pi equals our arc seconds. So let's put all of that into our formula. So I'll put all of that in. So from there, we'll take the answer from the previous calculation times by open brackets, a fraction 3,600 times by 180 divided by pi goes there. Execute. So therefore, the answer is 2.5, I beg your pardon, 2.5 arc seconds. So the limiting angular resolution of our telescope is 2.5 arc seconds. Now in the question, it says the seeing at the observatory is 0.75 arc seconds. Therefore, the resolution of our telescope would have to be better than 0.75 to take advantage of that. But we can see our limiting resolution of our 12 centimeter mirror is higher. It's at 2.5, so that's the maximum that it can see. And the question is asking us, can the telescope resolve our object as well? And our object, going back to our previous calculation, required a resolution of 1.6, but our telescope only has a resolution of 2.5 arc seconds. Therefore, the telescope will not be able to resolve the 1.6 arc seconds required. Now, have I done that correctly? I kind of hope I have, but I didn't in the exam, so I've got the question wrong anyway, so it's neither here nor there. But what do you guys think? Have I got that correct or not? The question then goes on to ask you, what is the reason the supernova cannot be located to the angular precision required? And I did put the answer saying the angular precision is smaller than the angular resolution of the telescope. So in other words, the telescope cannot resolve it anyway. And if you look carefully, the wavelength they say is 1.2 micrometers, which is, if we look at this diagram here, micro is around ultraviolet and X-ray here. And because our atmosphere mostly absorbs ultraviolet and X-ray, it says in the question, what would you do to be able to resolve this and to see this? And because our atmosphere absorbs these, the best thing to do would be to throw the telescope into space and do it there. So I effectively said that in my answer. It says here you can increase the diameter of the primary mirror, which you would increase the resolution of the telescope, relocate the telescope above the Earth's atmosphere, which again would allow you to see those particular frequencies better and that wavelength better. And that was kind of what I put for the answer. So let me know what you think. Where did I go wrong? Well, in here, I'm hoping I didn't go wrong, but you guys will tell me, I'm sure. Thank you very much for watching. If you quite liked this, I could do another one of these. Just let me know in the comments. If not, just say, Andy, you're a muppet, go away, which is fine also. Bye.